Okay, good afternoon. So we're here for a geometry lesson. We're going to continue on talking about two parallel lines cut by a transversal, which is what we started on last week. So let's jump right into an example here. It'll take me just a little bit of time to draw it. So let's see. Okay. Using this nice ruler. Okay. And a little bit of labeling here. So angle 1, 2, 3, 4, 5, 6, 7, 8. Oops, that'll be 14. All right, so these are 4 lines, 2 of which are parallel. These two, we'll call them W and V. This will be line P and line Q. So line W is parallel to line V. We also are told that the measure of angle 9 is 90, and the measure of angle 5 is 68. Those are degrees. We're going to try to find a couple of other angles here. Now, we should be able to find all of them, right? So we should be able to find all of these angles. Let's actually talk through them. Remember what our strategies are, what our tools are here. Well, basically, if two parallel lines are cut by a transversal line, then we have a bunch of sets of angles that are equal to each other for different reasons. So for example, just looking at this, and for now, we'll ignore this for just right now. We know, for example, that angles 1 and 9 are equal, 1 and 3 are equal, 9 and 11 are equal, 3 and 11 are equal. We also know angle 5 and 13 are equal, 7 and 15 are equal, 16 and 8, 16 and 14, and recall some of our reasons, right? Most of them revolve around the idea of supplemental angles, and then the idea of two parallel lines being cut by a line. So you get these corresponding angles, and then you get alternate exterior, alternate interior equal angles. So like 5, 7, 13, and 15 are all equal. 8, 6, 16, and 14 all equal. So if the measure of angle 9 is 90, then so is 11, so is 3, so is 1. What we want to be careful here, and what has changed in this question compared to what we looked at last week, is we have a secondary transversal, right? We have line P and line Q, both are transversals. So both fit this scenario of two parallel lines, W and V, cut by a transversal, P or Q. But that doesn't mean, and in this case they aren't, P and Q aren't parallel, right? It doesn't mean that they are parallel, they're just two separate lines cutting these two parallel lines. So each of them have the series of results that we want, but it doesn't mean, for example, that angle 1 and angle 5 are equal. They are not equal. P and Q are not parallel lines, so 1 and 5 are not corresponding lines, corresponding angles, because the lines P and Q are not parallel lines being cut by a transversal. They're lines that are not parallel. So let's find a couple, like angle 12. What then is the measure of angle 12? When you think about like what tools do we have at our disposal? We have the equivalent angle rules. We have also supplemental angles. If angles combine to make up an entire line or expand it across a line, such as angles 9 and 10 or angles 9 and 12, then they add to 180. So what we know here is that these two angles add to 180, and we know that angle 9 is 90. That means angle 12 will also be 90. So note here, we're actually in a very unique situation where 9 and 12 are equal to each other, but not by any particularly special reason as far as we're concerned. What's actually happening here is that line P is perpendicular to W and V. But that doesn't always happen, and we'll see that when we're talking about angles formed by line Q. So for example, let's look at finding the measure of angle 8. Well, angle 8 is supplemental with angle 5, which we know here is given to us. So that will make angle 8 180 minus 68. You can use your calculator if you need. 112. That means that angle 6 is also 112 degrees. Angle 14 is also 112 degrees. Angle 16 is also 112 degrees. Okay. So it's a useful question to be able to do. And so I think, yeah, let's do another one. First start by drawing our two parallel lines. That one, and then our two transversals. Now you don't have to have two transversals, but a question that has two transversals lets you kind of discern from a teacher standpoint if people recognize the limitations of or the meaning of the parallel lines, the how important that part is. So we'll name these lines R and S and M and N. And let me do a couple labeling here. 1, 2, 3, 4. And I'm labeling them differently in this question to force us not to memorize like certain angle numbers, or how they're labeled isn't the key. What their relationships to each other are is the key. The labels are just so that we can refer to them easily. Okay, so in this problem, we have that M, that line, is parallel to N. Okay, so these two lines are parallel. And the other two are not. R and S are not parallel, but angle 2 is 95 degrees, and angle 12 is, let's say, 72 degrees. Okay, so I'm not being precise. I'm not actually like measuring the angles. This diagram is helping us. It's helping us understand. We should be able to recognize the relationships between the angles regardless of whether this is like perfectly accurate measurements. Now, in some situations we would, and in many applied situations, we would need to be accurate if this diagram was actually meaningful in the sense that we were looking at some specific physical problem. But this is just an example. It's an abstract example. We can label, if I wanted angle 2 to be instead 98 degrees, that would be fine, right? Generally, you'll see that. Sometimes they're precise in a problem, but sometimes it's kind of an estimate. So like angle 2 is clearly an obtuse angle. That's somewhat close to 90, but bigger. All right. Now, let's find some angle measures and say why we know, right? And sometimes we'll have to maybe do more than one here, more than one reason. So first example, angle 10. What is the measure of angle 10? Be careful. The measure of angle 10 is 95 degrees. It's not 72 degrees. Right, angle 10 and angle 12 look like corresponding angles, kind of in the right position to be, except for that lines R and S are not parallel. So it is in fact the case here that angle 2 and angle 10 are corresponding angles. Okay. So we know the measure of angle 10. How about angle 8? Well, it's also 95. Couple of reasons why, but one we can say is because we now know what angle 10 is, it's an alternate interior with angle 10, which we know to be 95 because it corresponds to 2. Couple more. How about angle 5? So what I want to say is that angle 5 is 108 degrees. Why? Well, the first thing to remember is that really we're looking at M and N being crossed by S, right? We really want to think about the parallel lines being crossed by a single line. So that is the relationship here between angle 12 and angle 5. We're not that interested in the relationship between angle 2 and angle 5, right? So I'm referring again to the two that we know and trying to lead us to finding another angle measure. Angle 5 and angle 12 are going to be more related because M and N are parallel. R and S are not, so angle 5 and angle 2 aren't obviously related. Now, why is 5 equal to 108? Well, you can say it in a couple different ways. You could say, for example, that angle 12 and angle 4 are both 72 because they correspond, and therefore angle 5 is 180 minus 72 because it's supplemental to angle 4. You could also say angle 12 and angle 13 are supplemental, so angle 13 must be 108, and angle 5 corresponds to angle 13, so it must also be 108. Okay. So remember, when we're talking about corresponding, when we're talking about two parallel lines cut by a transversal, we get these series of equal angles. using different colors. So the reds are equal, the blues are equal, the greens are equal, the yellows are equal. Okay. Very good. Let's turn our attention then for a bit to what is kind of the heart of sophomore high school geometry and is a major part then of the integrated series as well, which is going to be triangles. I'm going to draw a quick triangle here as accurately as I can. This little straight edge is pretty helpful, but this part is the hardest part. We've got to try to line this up. That doesn't snap. So I'll do my best. There we go. And we'll call this triangle P. Actually, let's not do that for right now. Okay, so first of all, what makes it a triangle? Well, it has 3 angles, right? 3 internal angles or included angles. What are they? Well, angle 1, angle 2, and angle 3. They don't have to be equal. They don't have to take on any particular value. They do have relationships. None of them can be bigger than 180 degrees because that is the sum of the angles, internal angles of a triangle. And there are special triangles. All of them could be 60 degrees at the same time. That's an equilateral triangle, so all the angles are the same. You can have an isosceles triangle if 2 of the angles are the same. You can have a right triangle if one of the angles is 90 degrees, a right angle. And we'll look at plenty of those. And you will as well in all of your trigonometry be doing a lot of work with right triangles. But what we're concerned about are 2 concepts, and I'm going to do my best here. Concept of congruence. Okay. I think there's a way for me to grab this. Okay. Now what I did, and it's actually really useful to do this digitally, is I circled our original triangle, and I'm able to actually make a copy of it. So this triangle here is literally the same measurements in all ways as the original triangle, right? It's a duplicate of it. They are identical. Now, I'm not saying they're the same triangle in the sense that there clearly are 2 triangles, so they're not the same, but they are identical in the sense that all of their measurements are equal. They're just not located in the same spot. So I think sometimes we are pretty casual about our language, and we say things like they're the same triangle. Let's just be clear. Clearly, they're not the same exact triangle. One is over here, and one is over here, right? So they're not the same exact triangle. That can become maybe more obvious if... Oh, my mistake. Didn't expect that to happen. Let me make a different copy. There was a way. Not sure why that's happening. That's all right. That's all right. Let me make a copy for the last time here. Okay. So 2 triangles. So I'll practice this for next week, but I was rotating it earlier, but for some reason I'm unable to do that right now. Okay. What we care about when we're talking about 2 triangles and asking about are 2 triangles congruent? What we're asking is, could be translated in this way. If I were to lift one of the triangles up and orient it in the right way and set it back down, would it match perfectly with the other triangle, right? So if I were to lift this triangle up, is it possible for me to set it down, perfectly so it's literally on top in all ways of that original triangle? Well, these two, yes, obviously the answer is yes, because I made it, it is literally a copy that I could drag away from it. But, in most scenarios, you're given 2 triangles and asked, are they congruent? So you have to establish for yourself, is this type of behavior, this type of action possible, right? I'll notice something. If I draw a different triangle, like that, and I pick it up, that answer could definitely be no. We do want to hesitate here. This is why being able to rotate was very critical to this work, but okay, there we go, there we go. Oops. Reattach this. We do want to think about not just the same orientation, right? So this type of thing here, where I've been rotating it, is important to what we're thinking about, because it is possible to have congruent triangles that emerge because they're rotated from each other. Okay, so you can kind of see, like, as I rotate this, maybe they are congruent. So make sure you check, in all ways. No, still no. One thing I have to be careful with is when I'm pinching with my fingers here, they can change size, and I don't want to change the size of the triangle. But the idea is strong, right? You're trying to see whether a triangle maps to another triangle in some obvious way, so that all of the corresponding pieces are identical. So, for example, if I rename these, 4, 5, 6, rewrite that. Okay. Are these two triangles congruent? We're basically saying something here about correspondence between angles and sides of the two triangles. You have to be able to match equal angle to equal angle, equal side to equal side. Okay, that's what grabbing that one of these triangles and dragging it on top of the other and setting it down and having it overlay perfectly, that's what that means. Angles match with angles equally, sides match with sides equally. Now it is possible to have, say, angles all be equal, the sides aren't equal. That's a different idea called similar triangles. Also important for us, and we'll talk about it. But this is where we're going to start with the congruent triangle ideas. So what we need to be concerned about is, are angles on the two triangles, are all the angles equal and are all the sides equal? Right? And they correspond in the sense that if I lifted one up and twisted it the right way without shrinking or expanding it, just rotating it, I could set it down and it would match perfectly. And it turns out there's quite a few ways to shortcut this. But at the heart, okay, we need to prove that angle 1 is equal to some angle from this other triangle, 6, 5, or 4. We know that it's 6 because it's a copy. Angle 2 is equal to 5. Angle 3 is equal to 4. And these sides, this may be the right time to label this, A, B, and C, P, Q, and R. The sides are also equal. So for example, side BC is entirely congruent to side QR. Right? If I could snap this edge off, BC off, and pull it down here, it could lay right on top of QR and be exactly the same size and exactly the same orientation. So those two, we also need this and this. Now it's interesting here because, as I mentioned before with similar triangles, you can have the three angles be equal to three angles of a different triangle. They're not congruent triangles because, say, a triangle is stretched out or shrunk down. They're similar, but they're not congruent. If the three sides are equal, then they are congruent. Okay, and this is the first one of our postulates. It's called side, side, side. If there is congruence between sides 3 times on 2 different triangles, then they are identical triangles in different locations. Okay, so that's the first one that we're going to look at. We'll pick that up next week in our geometry lesson, which will be Wednesday. Looking forward to it already. Hope you have a good week, and if you need to join in for algebra, that'll be tomorrow, or statistics, that'll be